In this video, we're solving a buoyancy problem using Archimedes' principle, and we're given a bit of an unusual circumstance here. We have a block of iron that's actually floating in a cup of mercury. Now we notice that the density of mercury is greater than the density of iron, so if you took a piece of iron and stuck it in a cup of mercury, it would just float there on the surface. Now what we're trying to calculate is the submerged percentage of the iron. So to get started here, we want a force diagram for that iron block. And we have two forces acting on the block. We have gravity pulling down, as always. So I'm going to call that m times g, where m is the mass of the iron block. And we have the buoyant force pushing upward. And that buoyant force is determined by Archimedes' principle. In other words, it's equal to the weight of the displaced fluid. Now, before we get into any of the calculations, I want to give a quick reminder of density. So density is mass divided by volume. And we need to be able to really casually turn this around. So I just wanted to have this at the top as a reminder. This means that mass is density times volume. So now we look at a force analysis on the iron block, and the buoyant force pointing upward must be equal to the weight pointing downward for this thing to be sitting in equilibrium floating in the mercury. And that buoyant force is given by the weight of the displaced fluid. In other words, if we look at the submerged volume of this sample, I'll call that V sub, that's how much mercury has been pushed out of the way by the iron block partially sinking into the fluid. And we need to find the weight of that much mercury. So what we need first is the mass of that much mercury. And here's where we use our little expression, m equals rho times v. The mass of that mercury is going to be the density of it. So the density of mercury multiplied by the volume of mercury that was pushed out of the way as the iron block sank into the fluid. So that's V sub. All right, so that's the mass of the mercury. And if I multiply that by G, I get the weight of the mercury that's been pushed out of the way. Now over on the right-hand side, we have the mass of the iron block, but it's going to be useful to re-express that as density times volume as well. So we're going to call the volume of the entire iron block just big V, and I'm going to write rho of iron, chemical symbol Fe, times big V for the volume of the entire iron block. That's the mass of the iron block. And we still have to multiply that by G. So notice that the G's are going to cancel on both sides now. And what we're looking for is the submerged percent of the iron. So what I want to do is actually divide both sides by V and find an expression for V sub divided by V. So that gives me the fraction of the block that's submerged, and then we just have to convert that into a percentage. Well, solving for V sub over V gives me rho iron, rho Fe, over rho mercury, rho Hg. And those are the numbers that we were given in this problem, so I can go ahead and plug them in. The density of iron was given as 7,874 kilograms per cubic meter. The density of mercury, 13,546. And as a decimal to 3 significant digits, that's 0.581. And as a percentage, that's 58.1%. So if you're lucky enough to ever be able to run this experiment with a giant cup of mercury, you can expect a sample of iron to sink just slightly more than halfway down before it's supported by the buoyant force and just floats there on the surface. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.